finished your vote. And if is there anyone who could not finish their vote, then please let me know. So my question to you is that whether there is anyone who could not finish his or her vote. May I assume that everyone finished their votes? Okay, then we may start today's lecture. So, and also another thing that I would like to talk about is some opinions of the students and some requests from students regarding to these online lectures. So I received that opinion related to this reliability engineering course, and of course it consists of four questions, and some of your feedback or opinion about the online lectures, your midterm exam, and how to assign your final score, and whether offline lectures are necessary or not. So let me briefly finish one by one. So maybe the easiest one would be whether online lectures are necessary or not. And of course, most of us agree that online lectures are necessary. Just the single reason that we cannot do the online lectures is that we is because we want to follow the guidelines provided by the government to protect ourselves, to prevent widespread infection of people in this country. And as a way of preventing that, we are currently doing this difficult online lectures. So of course, these online lectures are scheduled to finish on eighth weeks. That means on the week of a midterm exam. And then we hope that we are able to have that face-to-face offline lectures. But of course, it depends. We need to follow the guidelines provided by the government and the policy decided by the university management. Another one is that about the feedback or your request about online lectures. One opinion is that is that this the use of this real-time YouTube broadcasting has some limits because giving questions, raising questions, and receiving feedback is not. So there is a certain limitations in providing raising questions or providing feedback about the lectures. So I wonder whether we need to change the platform for these online lectures. So this would be the fifth week of giving online lectures with this YouTube framework, YouTube platform. But maybe if students or believe that the use of Zoom platform is more preferable, then maybe I may think about that. Of course, another factor that we need to think about is that we also need to adapt to another platform. Of course, most students may be familiar with that Zoom platform because other real-time lectures are already given in that Zoom platform. But at least I want to I would like to express my opinion about the use of this YouTube platform is that when I first started this online lecture, mm, I worried about the the how- worried about that heavy traffic that such a online platform like Zoom platform might cause because it is bidirectional. It requires bidirectional or multidirectional communication. So it may impose some severe heavy load on our network traffic, and related to that, this on YouTube platform will require much less resources on network traffic. Mm, and of course, after tomorrow, the online semester will begin for elementary school students and middle school and high school students. So the problem of traffic will become more severe. That's what I'm expecting. So maybe if let's first see whether the how can I say network whether that online environment is uh, is able to endure that heavy traffic or not. Let's first see, and I'm going to decide and let you know whether we are going to give two more online lectures with this YouTube platform, or maybe we we need to move on to another platform like Zoom platform. And there is another request about uploading the recorded version of these real-time lectures, and I have certain opinion about that. So the thing that I'm concerned about is that if I decided to upload the recorded version of this online lecture, then the attention of students may be somewhat diverse. I mean, people will there is some students who feel difficulty in concentrating on these real-time lectures because maybe students may think that they will have another time or another chance to study these contents with the recorded version. So if we consider the pros and cons of uploading that recorded version, so the the thing that I decided is that I want students to clearly focus on these real-time lectures. Of course, we might have experienced some difficulty in in YouTube streaming due to some heavy network traffic problems. But basically, I basically would like to ask you to concentrate on these 3 hours of online lecture first, and then mm, if you have any questions or if you think you need to learn more about that, then you may raise questions, or you may ask you may mm, yes, you may ask questions, or you may study more after the lecture is over. So, but uh, so that's base my base position about this request. But of course, if students may, but another thing that I'm considering is that I'm going to assign some short period of time, and then during that time, maybe I may uh, allow students to uh, listen to these lectures once again, so that they are able to. So if they think they need to study more on some specific topics, then they will look for that topic in the kind of recorded version of that. So the answer for this would be I'm currently considering about assigning or assigning some specific time period that you will be able to study on some specific topics. Of course, that time period will not be very long, so it does not mean that you are going to take all the lectures during that time. But if you have several important questions and you would like to review what was discussed during the lecture time, then you may utilize that time period for that purpose. So midterm exam, and I'm not sure whether the opinion is the opinion provided to me is the opinion of one or two students, or it is a kind of a general opinion about midterm exam. But what I realized is that the opinion given to me, by seeing the opinion given to me, it seems that at least some students are reluctant to taking midterm exam on the basis of take-home exam form. So some students may feel that it is not fair and substitute that midterm exam with some homeworks. Okay. So at this point, maybe this can be so. First of all, I'm not sure whether this would be the opinion of all the students in this class. But of course, I'm going to think about, by assuming that this is a kind of a majority opinion of the students, I may think about substituting midterm exam with some homework problems. But honestly speaking, I cannot exactly find out the difference between take-home exam and some homework problems. So of course, I'm going to think about that. Even though I already reported to our department office and our management that I'm going to take the midterm exam in the form of take-home exam. And related to providing you grades, some students prefer absolute evaluation, and other students prefer relative evaluation. So this is something that I'm going to decide. But of course, after taking course, there's some way that I need to distinguish between those students who studied very hard and those students who studied less hard. So I basically prefer providing that kind of distinction between different groups of students. So these are kind of my answers to your opinions and requests about these online lectures. Okay. Another thing that I would like to one thing that I would like to talk before we get into our topic. Today's lecture topic is that it is a kind of my personal opinion on you should what you should study, and then what you need to be able to as a student studying in an engineering school. So first, let me call it as so if you study in an engineering school, and if you so let me write it as capability expected for an STU student in an engineering school. So of course a lot of students wants to be hired by many different companies, and then I would like to ask you to think about what capability those companies are expecting to you. And first, so of course some basic capability is that this is not for the engineering students. It is some kind of a basic capability or basic skills that are required to all the students. So of course you should be able to sufficiently you should be able to utilize a word processor like Microsoft Word or HWP, and also spreadsheet software like Microsoft Excel. And another one would be some presentation tool like Microsoft PowerPoint. These would be some basic skills that you will need to have. And also among them, I would like to emphasize the importance of utilizing spreadsheet. So because so this is related to the second capability. If you studied engineering, then people will expect you to be able to to be able to handle some numbers. In fact, a lot of numbers. So for that purpose, spreadsheet software like Microsoft Excel will be very useful to do the work. So if you not feel comfortable in dealing with the numbers, then you might experience in adapting to what is expected from companies. There would be some advanced. So this would be the basic skills, and of course these will be the basic skills will be those capabilities that any companies will ask you. And if you want to study more, and if you have a higher level of capabilities, then I would like to recommend you to utilize some mathematical software, mathematical tools like MATLAB or any other software that you may prefer. So this would be the example. Mm, this is the one that we are going to. So if you believe that we would like to we would like to study, or if you would like to study some joint probability distributions, then I hope that you are also able to draw these types of figures with Microsoft Excel. Of course, or so these are the examples. So when we study the binomial distribution, then of course you may confirm what you actually studied with this one. This is about hypergeometric distribution. When we study Poisson distribution, then you can actually apply the knowledge that you studied during the lecture time and then use it to clearly understand what was learned during the lecture time. So just listening to, I would like to say, just listening to lectures will not give you a perfect understanding on those topics. So the only what you need is actually apply those theories, and then you need to handle and try to apply it and see what could be obtained, and then see whether what was obtained is consistent with what you learned during the lecture time. So these types of things will be required for you to completely understand what is told or what is dealt with during the lecture time. So without practice, without these types of practice, it will not be easy for you to understand this. So that is why so when we study this types of graph, these types of joint probability distribution function can be drawn with this software, Microsoft Excel, or if you would like to so or if you let me slightly change the size. The size of a font. Okay, and on almost exactly same figure can be drawn with this kind of mathematical tools, and of course you are able to, if you need, you are able to rotate this. So these mathematical tools will help you understand what is learned, what is told during the lecture time. So I would like to recommend you to raise these types of capabilities of dealing with the numbers. So basically, you learn a lot of mathematics. So my point is that I want all of you to, so mathematical tools will be helpful in, so you learn theory, and or but after learning theory, you need to understand how that theory will be implemented or applied to the real world. So with this in mind, so the emphasis is that this will be the these will be the basic skills, and of course you will be able to you will be asked to be able to deal with a lot of numbers and the mathematics associated with that. And if you pursue higher education, then or if you have more advanced capabilities, then I would like to recommend you to learn how to or how to utilize these mathematical tools. And of course, I would like to ask you to be able to very comfortable with utilizing these tools. So let's go back to today's topic. So last time we started from section 2.5, and it is basically about estimation and hypothesis testing. And we have two different kinds of estimation: point estimation and interval estimation. So as its name says, point estimation just provide you just one single number, and you do not know how accurate that number will be. So because of that, in case of interval estimation, instead of providing instead of providing one single number, we provide a range of numbers, and also something called some percentage called the confidence interval or confidence level associated with that estimation. So there basically we have two different approaches for providing estimations. So let's first, before get into that estimation topic, so let's first try clearly understand those notations that is used in this textbook with an example. So in this text, it says, let's suppose we are interested in estimating a single parameter distribution, and x and theta. So last time I provided you this example. So single parameter distribution. So single parameter distribution is represented with f of function f of x and theta. So here x is the parameter. So in case of exponential distribution, x is the parameter for the random variable. So in this case, if capital random variable is timed to x, and this small x is assigned to indicate a specific value of random variable. And related to this zeta, in this case, in case of exponential distribution, lambda, so because exponential distribution is a single parameter distribution, because in exponential distribution only one single parameter lambda is used to determine a specific exponential distribution. So we also learned several two parameter distributions. Like normal distribution requires two parameters, mean value and standard deviation. And gamma function also requires two parameters, alpha and beta. Weibull distribution also requires two parameters. So just like that. In that case, we need two parameters there. But in case of single parameter distribution, x is the parameter for random variable and zeta would be the parameter. Zeta would be the parameter, that single parameter. And currently the problem that we are dealing with is that we know, just one example is that from the experience, we know that the time to failure follows exponential distribution. But we do not know the exact number for lambda. So this zeta is the target for our estimation. So we do not know lambda, but we have some samples. So from our previous experience, let's assume that we have n number of random samples. And from these random samples, this single parameter lambda can be estimated. So this process is called as estimation. And if we provide just a single number for lambda, then that is going to be point estimation. So let's move on to our textbook. So that is the meaning of a single parameter distribution. X and zeta would be the parameter that we would like to estimate. And we have random samples. And t is a function, a single valued function of these n different numbers. And in that case, t is also a random variable. So what it means is that x1, x2, and xn, all these samples, they are not determined. They will also change. So because x1, x2, and xn may change with associated probability distributions, so this t may change. So if we move back to our notebook to see single example of that, so t may be defined like this. So in this case, you may see that t is a single valued function of x1, x2, and up to xn. So this t is referred to as a statistic, and in the form of a function, in this functional form, this t is called as estimator. And with these actual numbers, if we calculated some numbers from numerical numbers of samples, so for example, if we by using this function, we calculate that t equals like 10 per hour, then that would be an estimate. So these are the meanings of statistic and estimator and estimate. And next, unbiased. So, on estimator, so unbiased, of course, being unbiased is a good property of an estimate. And so, if we have this estimate t, so t is an estimator, and of course it is also a random variable. That means depending on the numbers. So with the first 10 samples, we are going to get one estimate. With another set of samples, we are going to have a different estimate. Of course, the first estimate and the second estimate would be different. And also, with another samples, with another set of samples, we are going to get another estimate. So, estimate actually varies. That means estimates or estimate like t is also a random variable. It does not have one single value. It may have many different values, and probabilities or probability distribution will be associated with this. So if t is a random variable, or if t varies, but at least one preferable property would be at least each time for different samples we are going to get different estimate, but we would like to, it would be preferable if its estimate, if its expected value or its mean value becomes the parameter that we are trying to estimate. So in this case, it is called as unbiased estimator. So we hope that these estimates and or estimator are unbiased. So we are going to see an example later. We are going to see an example of a biased and unbiased estimator. So let's move on to our textbook. So unbiased estimator is the case when its expected value equals theta. So the theta is the parameter that we would like to estimate. And it also talk about some different properties like efficient and sufficient. And I'm not going to explain all these details. So let's move on. So currently we are talking about point estimation, and the first approach for point estimation is method of moments. So how can we calculate some estimates? And it tells us one way of doing that is to use method of moments. So we are able to define, maybe we are able to define the sample mean like equation 2.127, and maybe sample variance like the one in equation 2.128. So these are the functions with xi's. So these are estimator. And so xi, we want this sample mean to be an estimate of the real mean value, so-called something called the population mean. So here x bar and sample variance can be used as the point estimates of the distributions mean and variance. So we decide this estimator and we hope that this becomes the estimates of mean value and variance. But previously we hope that so let's move on. Let's go back to our textbook, notebook. So the first approach was methods of moments, and before calculating sample mean, let's find out the sum of when I equals 1 to n, what would be sum of xi? Of course, sample mean is calculated by dividing this sum with the number of samples. And let's think about the expected value of this. What would be the expected value of this? So this would be same with expected value of the x1 plus expected value of x2 and so on. Expected value of xn. And expected value of x1, because we took sample from the population whose mean value is mu, then the expected value or the mean value of x1 would be simply mu, because we took sample from there. And then expected value of the last term would be mu. So we are going to have n number of mu's. So because of this, if we divide both left and right hand side with n, we can say that the estimate provided, the sample mean equation provided in our so if we rewrite this, so the point is that this is the sample mean equation, and expected value of a sample mean equation would be mu here. So that is, this estimate for sample mean is an unbiased estimator. It is unbiased. However, in case of a sample variance, how do we calculate the sample variance? And another thing that I need to emphasize is that previously we learned about the first moment about the origin, or second moment about something, first moment or something. So what we calculated here is that in fact we calculate xi minus 0, and we did not put power on that. So the sample mean equation is in fact the first moment. So it was calculated by the first moment about the origin. So first mean could be calculated with the first moment about the origin. What about sample variance? In case of sample variance, we are going to calculate, because currently we are talking about method of moments. So the sample variance is estimated by using the second moment about the sample mean. So to do that, we are going to calculate. So second moment about sample mean will be, parenthesis, and xi minus, we calculate if x bar is the sample mean. And because it is a second moment, we are going to take the square of it. And so if we divide this with n, as let's see. So if we divide this with the n, that can be another estimator for sample variance. And with this equation, give us the second moment about the sample mean. The problem with this estimator is that it is this estimator of a variance is biased. This estimator is actually biased. So this is because, so we are going to take the expected value for this. So the expected value for only these parts will eventually, of course it can be easily proved, but I'm not going to provide you all the details about this. But eventually you are going to get n minus 1 sigma squared. Sigma squared. So if you divide this part with n as the equation in 2.128, then the expected value, if we divide both left and right, if we divide both left and right hand side with n, then we are going to get the that expected value will not be exactly sigma squared. The expected value will be n minus 1 over n sigma squared. So because of this, so if we divide both sides with n minus 1, then the right hand side becomes sigma squared. So in that case, this estimator has a very nice property of being unbiased, because the expected value of the estimator is the parameter that we would like to estimate. So that is why we use equation 2. Let's see. That's why we use equation 2.129 instead of 128, we uh, divide this with n minus 1 instead of n. Of course, if we exactly know the population mean, then in that case we should divide this, and in that case, to calculate variance, we should divide this with n. But when we use sample mean, then we should divide this with n minus 1. So these are about method of moments. You may practice this with example 2.27. Another approach for finding point estimate is maximum likelihood method. Maximum likelihood method. So this is one of the most widely used method for estimation. So just like the case of exponential distribution, consider a continuous random variable x. In the example that we frequently use, x would be the time to failure of any component or any product that we purchased. So time to failure, the time until that product fails, would be the random variable, and the probability density function would be x is the random variable, and theta, in case of exponential distribution, lambda would be the parameter that determines that exponential distribution. And let's assume that we have n samples. So we have these samples x1 up to xn of size n. And of course these samples came from this random variable x. That means these are samples of the time to failure, the time until that product fails. So we would like to estimate theta. In case of exponential distribution, we would like to estimate lambda. And we would like to estimate lambda in such a way that that value of theta delivers the highest probability density of observing the particular set of samples. So already we have these particular samples. And of course these samples can be obtained from different numbers of parameters. And because even if lambda is a very small value, but obtaining these samples are possible, just the probability would be very, very low. Or if the lambda is extremely high, but obtaining these samples are still possible, just the probability would be very, very small. So we would like to find the theta, the value of the parameter that maximizes that likelihood or the probability of observing this set of samples. So that's the basic idea behind this maximum likelihood method. So currently we do not know what theta would be. So theta is currently a variable. In case of exponential distribution, this would be lambda. And x1 would be the time to failure of the first sample for time to failure. And small f is the probability density function. And if all the samples are assumed to be independent of each other, then this likelihood is calculated as the product of all the probability density functions. The second one is the probability density function of observing x2 when zeta is the parameter, and so on. So we are going to multiply n number of probability density functions. So how can we calculate that? This maximum likelihood estimate is calculated, is chosen as the one that maximizes the likelihood function. So we do not know exactly the shape of the function. However, see, let me, okay. Okay, let's assume that this would be the function for likelihood. So what we just calculated is, I'm sorry. So while varying this value of zeta, we so that would be likelihood function, and this is in fact a function of zeta. So if this is the shape of the function, this likelihood function, how can you find is the value that maximizes? How can you find the zeta that maximizes this likelihood function? So that would be so we would like to find this point. So we would like to find out this point, and this can be found, this can be calculated by finding the derivative with respect to the derivative of L, which is a function of x1, x2, and xn, and also zeta, with respect to zeta. So we would like to find out the point or the value of lambda that satisfies that this becomes 0. So this is a function of zeta, but for this specific zeta, we would like call this as zeta hat. Maybe I need to increase the size. So this is basically what we would like to do. So let's move on to our textbook. So in fact, L, the likelihood, is not only a function of zeta, but also a function of all the samples. And we would like to calculate this. We would like to find out the point that its derivative with respect to zeta becomes 0. And in many cases, it is not easy to find out this point. So in many cases, in fact, it is more convenient to maximize the logarithm of likelihood function. So if you remember what log function is, it actually always gradually increases. So because its log function is an increasing function, the value, the zeta that satisfy, or the zeta that maximize the likelihood function, will also maximize the log of likelihood function. So we are going to see an example for that. So this was example 2.28. So example 2.28. Let's see. Yes, we have this function. So exponential function is the one that we are currently dealing with. So let's first read the example first, and then try to solve it. So we have n samples t1 up to tn. These are time to failure data of a component whose time to failure is assumed to follow exponential distribution with parameter lambda. And with these samples, find the maximum likelihood estimator for lambda. So this is basic probability density function, and the samples provided are let me use this one. So but this time is time 1 t2 up to tn. So we have n samples for time to failure. So let's see this as not only function of x, but also function of lambda, and the likelihood function. So the likelihood function is calculated as L and of course the likelihood is dependent on all the samples and also lambda. And if you remember that likelihood function, it was given as f t1 t1 lambda and t2 lambda up to tn lambda. And because we know this function, so maybe we may change this to time t instead of x. So t1 lambda would be lambda exponential minus lambda exponential to the power minus lambda t1, and the second one lambda exponential to the power time lambda exponential to the power minus lambda t2, and multiplied with, it goes on and until it becomes to the power n. And because the samples are already given data, so t1, t2, and tn are all the given numbers. So basically this likelihood function is a function of lambda. Oh, sorry. So if we see this example, so we are going to have how many lambdas do we have? How many lambdas are multiplied here? There are n lambdas. So lambda to the power n. And if we collect all the exponential parts, then it is going to be t1 plus t2 plus, goes on and on until it becomes tn. So this is basically, this is in fact the likelihood function for this problem. And because it is not easy to find out the lambda that maximizes this likelihood function, so what about finding the derivative of this? So if we see this likelihood function as a function of lambda only, because these are all, in fact these are all constants, so instead of in fact we are able to I think we are able to calculate this for this specific problem. So take derivative. So if we directly take derivative of this, then it is going to be, so the take derivative of this would be n multiplied with n to the power minus 1 exponential term plus this time lambda n and this part minus n, that would be lambda n exponential minus n will become 0. So this would be the derivative with respect to lambda, and from our previous figure that I just showed you here, so we would like the point that makes this derivative 0. So zeta hat is the so if we write it exactly, then it should be written in this form. So when lambda becomes lambda hat, then it should be 0. So this exponential term will disappear, and here we are going to have n only n. So what will remain is that only n. So we are going to divide. So it becomes 0 when for this estimate of lambda. So for this specific value of lambda, this is satisfied. This should be satisfied. So maybe here so we may in each term, in the first and second term, we delete this exponential part. So we may delete this exponential part, and then we divide each term with lambda hat to the power m minus 1. Then it is going to be simply become what? Only one lambda will remain here. One lambda will remain. So that means this is given as n divided by the sum of all the time. Sum of all the time to failure sample data. So now we have the estimate for lambda from all these sample data. Of course, it is also possible that we calculate, instead of this, we may calculate log of this. Of course, it will be also possible that we calculate the log of likelihood. Of course, we will get the same answer for this. So from here, of course, it will not be very difficult. And here minus this. Minus exponential. This should become 0. And minus here comes 0. this would be simply log of lambda, and we should find derivative for this, d lambda. Now it becomes, so log of lambda would be, so n is a constant, and derivative of log of lambda would be 1 over lambda minus, so lambda will disappear, so derivative of lambda would be 1, so only this will remain, and lambda hat would be the one that make this term to become 0. Of course that would be n over, so we are going to get the same solution for this. So this is how maximum likelihood method is applied. So I hope you are able to understand, of course not only understand what is, how we apply the basic theory about this maximum likelihood method, and then you are also able to actually apply to real world problems. So it's already 4:19. We are going to have about 15-minute break from now on. So we are going to start a lecture at 4:35. So of course, as always, I would like to ask you, all of you, to leave your name to check your attendance. Then based on some sample data, we would like to estimate the parameter, the unknown parameters of some distributions. So what we just studied was point estimation. So from point estimation, we are going to get just one single number, and to get that single number, we just studied two different approaches. The first one was method of a moment, and the second is maximum likelihood of method. And as the textbook already mentioned, the second one, maximum likelihood method, is one of most widely used method for not only in estimation but also in many maximization problems. And now, second, we are going to move on to interval estimation. Interval estimation. So first, we are going to cite it. We are going to first talk about two-sided confidence interval. So of course we are going to, so from this, so previously the unknown parameter theta was given as a point value, but this time we are going to provide some interval instead of a single point number. And when providing interval, then if we provide a very narrow interval, then the possible probability associated with that interval will be very small. And if we as we gradually increase the interval, then it is likely that the unknown parameter belongs to that interval gradually that probability gradually increases. So the expected probability that the unknown parameter belongs to that interval is called as a confidence level. And this word, the confidence interval, tells us that for a specific confidence level, the interval specified, I mean, the confidence interval indicates the interval specified or associated with given confidence interval. So for example, the interval is given, and then if 95% is associated with that, that can be called as confidence interval. And by the word two-sided, we are going to have two numbers. The two-sided means that we are going to have the low limit and upper limit. If it becomes one-sided, then one limit approaches to 0 or infinity, and we are going to specify only lower limit or upper limit. So in case of, let's first see two-sided interval case. So with this, what we would like to calculate is theta is the parameter that we would like to estimate. And this time, theta is given as 2. So instead of a single number, on estimate and an interval is provided. So this on interval, the two intervals, the lower limit and upper limit will be provided. Of course, this lower limit and upper limit should be calculated. So if we have a so let's use this instead of this. Let me find the one that we can utilize here. So it is going to be, if we have n samples, then the lower limit will be also a function of all n samples, and also this upper limit will be function of, that means the lower limit and upper limit should be determined by these samples. And if we increase, as I already mentioned, if we increase the interval, then it is more likely that the true value theta belongs to that interval. If we specify very narrow interval, then the probability that this theta belongs to that narrow interval will be small. So after specifying this interval, then we need to provide the probability associated with that. So usually the probability is given as 1 minus alpha. So if alpha is 0.05, then the probability will become 0.95. Then in that case, so as an example, when alpha equals 0.05, then it can be said that the interval given by the lower limit and upper limit, that interval provided with these two limits will be, in other words, the parameter that belongs to the interval between the lower limit and upper limit will become 0.95. Then the interval given by these two limits will be called as 95% confidence interval. So in this case, this will be called as 95% confidence interval. And 95% is called as confidence level. So of course, if alpha becomes 0.01, then the confidence level will become 99%, and the interval specified for that case would be 99% confidence interval. And this is the case of a two-sided case. Of course, it is also possible that we provide one-sided interval. So for example, let's write it down, one-sided confidence interval. So the form of given is that in case of one-sided interval, then the first case would be we only provide upper limit and lower limit starts from 0. Or it can be in such a way that so let me use this. It can be such a way that we only provide so in this case it provides only lower limit so this would be 1 minus alpha. So in this case, theta u will be called as a one-sided upper limit, and in this case, theta L is going to be called as a one-sided lower limit. So how this general theory can be applied to specific distributions. So let's think about normal distribution. I hope students may have experience of dealing with a normal distribution. So let's do some example. So what would be if x is located between so starting from mu minus 1.96 sigma and mu plus 1.96 sigma. What would be this probability? In fact, this would be the probability of this would be 0.95. So I hope students also have experience with this. So in case of it approaches almost the 3 sigma, then 3 sigma, then the probability almost approaches to 0.99. So how can we find that? GMT distribution. I'm trying to find out the number associated with 99%. 99%. Okay, I will let you know later. So what value make this number 0.99? So I hope our inverse. This would be norm standard this inverse. 5 would be 1. So 1.96. I'm sorry. 0.95. 1.6. 0.975. Well, that's approximately. So 0.965. So if we would like to find the value for 0.99%, then we are going to need this probability. So 2.56. 2.56 of sigma will give us this. So the reason I try to find out this 99% critical value is that so what we can see here is that as we increase the interval, then the probability, so as we increase the interval from 1.96 sigma to 2.56 sigma, then this probability of having x inside of that interval actually increased. And this will be also true when we actually perform estimates on this. So when, let's see, so we are going to divide the cases when we know the variance and when we do not know the variance. So when we know the variance, Then of course variance can be used. Variance can be used for so when variance is known, then we are able to apply normal distribution. And the variance, the known variance, can be used to estimate the intervals for this. So when variance is known, we are going to apply the normal distribution. So to do that, so from samples, so the situation is that from the samples x1 to xn, of course let's assume that we have x bar, that is the sample mean. So if we have the x bar, the sample mean, that will be of course one of the sum of all the samples. Sum of when I equals 1 to n and xi. So this is sample mean. So sample mean can be calculated. And if we know the sigma, if we know the variance, then we are able to also calculate the variance, or in this case the standard deviation. Let's think about variance. So if we know the variance of x, then this is the variance of sample mean. So when we took n number of samples, and this sample mean is given as the mean of x, the population, divided by number of samples. Of course, this means that the sample mean, I'm sorry, the sigma of x bar, that's standard deviation of x. Standard deviation of x would be sigma, that's the standard deviation of the population divided by square root of the number of samples. And so with this n number of samples, we would like to estimate the interval that the population mean, this mu, belongs to. With n samples, so in other words, with n samples, we are going to calculate the sample mean, and by using sample mean and here the various already known variance of the population, then we would like to estimate the interval in which the actual population mean mu is located with the probability associated with that. So to do that, so we know that this sample mean is also a random variable that in fact follows normal distribution. So it has so this sample mean also has the mean value. So sample mean will be located around the population mean. So if we minus mu, so if we standardize the distribution for sample mean, then this is what we are going to get. So this random variable, normally distributed random variable, minus the mean value or expected value of this random variable divided by its standard deviation. So we actually normalized, we standardize this normal distribution. Then in that case, it should belong to our normal distribution. I mean, the table for normal distribution should be applicable to here. So for example, so the probability can be, so just like we could provide the interval is associated with this probability, we are able to provide that this becomes a 1 minus alpha. So if this is the 1 minus alpha, then in the standard normal distribution, which is usually denoted with z, it should be minus of 1 minus half of the alpha value. So what it means is that, and also because this is a symmetric, the right hand side would be the plus value. So let's try to explain this normal distribution. So this is a normal distribution, and this red color is the standard normal distribution. And so the value, so if we would like to include 95% of this, then it almost for 95%, then it should start from minus 1.96 sigma to 1.96 sigma, because this distribution is a symmetry with respect to the mean value. So for that purpose, let's see the Excel file. So what we tried to do was that when alpha is given, so if alpha is given as 1.96 0.05. That means confidence level the confidence so the confidence level would be 1 minus this alpha value, and we would like to find out the lower limit and upper limit for this in this case. So lower limit and upper limit. So because 95% is included, once again, so we are going to move back to this graph. So for 95% to be included in under this graph, so if we would like to find the two, we would like to find the two points, then usually the normal distribution value is given from the integration from negative infinity to the point of interest. So, so the point that we need to find is first, so here, once again, so if we want the 95% to be included under this curve, then the right hand side from the mean value, then we need to have the half of 95%. So that would be 0 point. The half of 95% would be, so lower limit. How can it? So lower limit to find the upper limit. So from the point of mean value, in this case, in case of a standard deviation, it would be 0.5 plus 0.97. We need 0. The half of 95%. So this would be the value that I look for. So maybe we may so in other words, another way of seeing that is that so let's go back to here, and if we want to find out the interval that includes 95%, then 95% will be included inside or under this curve. That means 2.5% will be included in here, and also the remaining 2.5% will also remain here. So another way of seeing, another way of finding that interval for 95% is that this is the point where the 2.5%, which is half of 5%, is located to the right hand side of that value. So in other words, this is one way of calculating. Another way of calculating the upper limit is that we would like to find 1 minus, in the right hand side we need half of the half over 5%. So that will be this number. What about the lower limit? Oh, I'm sorry. This should be the upper limit. So let me slightly modify this. So probabilities should be assigned. This should be assigned. So 0.95 So 0.95 should be calculated as 1 minus half of 5%. That is 1.96 of standard deviation. So this is why we have this value of so in the right hand side, in the standard deviation, we should find out the value that give us 1 minus half of alpha would be the upper limit. And to the lower limit, because normal distribution is a symmetric with the standard normal distribution is a symmetric with respect to 0, then so because this standard normal distribution is a symmetric with respect to 0, and we would like to find the lower and upper limit is located here, and then because it is symmetric, minus of that value will give us the lower limit of this. Of course, the integration from 0 to this lower limit will be that probability would be 2.5%. The probability over that upper limit will be also 0.25%. So if we add the two extremes, then that will be 5%. That 5% is the value for alpha. So this is why it is the right upper limit is decided like this. The value of 1 minus alpha over 2. And the lower limit is given as minus of the upper limit. So if we know this, then we are able to find out the interval for mu. So how to do that is simply we are going to multiply this standard deviation of a sample, and also here multiplied with that. Now it becomes the equation for this. And then next we are going to so to help your understanding, we are going to subtract this x bar sample mean to all three to the left and right hand side, or in each term we are going to subtract the simple mean. So that means, so now it becomes minus x bar and also minus x bar plus this. And next is that we are going to multiply minus 1 to all the terms. then multiplying minus will change the direction of inequalities. So multiplying minus, what we are going to have, plus, and also plus, and now it becomes minus. And we should now change the direction of inequalities. So if we rewrite this, if we rewrite with the direction of inequalities that we are familiar with, then it becomes like this. So what does this mean? What this equation means is that currently we know the sample variance. We know the variance of the population. We know the variance of the population that this n number of samples were taken. And we do not know, even though we know their variance, we do not know the mean of the population, this mu. We do not know where the population mean is located. And through this process, so we know the variance or standard deviation of population. We know the number of samples. We know we can calculate the sample mean. And these are the values associated with this alpha value. So, for example, if alpha is 5%, then this becomes 1.96. If alpha becomes 1%, this becomes 2.56. And what it tells us is that we can specify the interval that this population mean, mu, belongs to. So, as this number indicates, for 99 if we have a confidence level of 95%, then these values will become 1.96. If we place alpha equals 0.011%, then we are going to have a much wider interval. When the confidence interval becomes 99%. So from sample mean, we are able to estimate the interval in which real population mean belongs to with the confidence level. So what if this is the case when we know the variance? What if we do not know? Sigma squared is not known. What if we do not know the variance of the population? In that case, we are not able to apply normal distribution because the variance should be calculated. So in this case, of course, the way we calculate sample mean will be same. However, because we do not know this variance of the population, we should calculate the sample variance. So how can we calculate sample variance? Well, we already have this. So s squared, that is this is sample variance. And now this time the variance of or in this case the standard deviation of sample mean is estimated by using sample variance. And as I already mentioned, we are not able to use the normal distribution, but in this case we should use we should use students' t distribution. So if we very similarly, if we rearrange this, of course this time we should use sample standard deviation instead of the standard deviation of the population. So then we are going to have the result that is very similar to the one that we could get in our previous case. The difference is that but instead of moving on, so one thing that need to be mentioned is that we have a different our table for this normal distribution and standard deviation. These tables have different ways of providing the numbers. So let's see Appendix A. So in case of standard normal distribution, the data provided here is the area under this standard normal distribution, but starting from negative infinity to this value. So that means integration from negative infinity to -4 would be this value, and so on. So in case of a standard normal distribution, this tabulated value is given as the integration from negative infinity to this value of z. But in case of students' t distribution, the number is provided in somewhat different way. So yeah. So this is the case for standard normal distribution. T distribution. So maybe we better use when the samples are, we have a lot of samples. When the number of samples are sufficiently large, when the samples are sufficiently large, then this approaches to normal distribution, and unfortunately I can see some discrepancy. See some discrepancy between what is written in the textbook and what this tabulated value. So between the what is written in the textbook and what is provided in the tabulated values. One-sided limit. Down. Well, now I see that, so from this table what is written is that from for one-sided limit, so the probability, the value of t, that probability becomes 0.975, now becomes 1.96. So in fact t distribution is given in the exactly same way as the normal distribution that we have seen. So in other words, this table gives us the value of t distribution that's the same with this graph. So in that case, so this would be valid. This equation will be valid, and let's check our textbook. So that means this is not correct. So because the way t distribution value is given are same, then this one should also be 1 minus half of alpha, and this also 1 minus half of alpha. What I mean is that so this is the valid equation, and if we do the same manipulation, then what we are going to get is this would be t, and we are going to use the sample standard deviation t and sample standard deviation. If we follow the way t distribution is given, t distribution value is given in this textbook, and the equation that is given in our textbook will be valid only when t distribution value is given in somewhat different way from the area under the area from the right side tails. So that means and frequently t distribution is given in that way, the area from positive infinity to the from positive infinity to the t value of interest. In other words, from t value of interest to positive infinity, But in this case, so in this textbook, t value is given, the table is given from negative infinity to the t value of interest. So in that case, this would be the valid equation. So when sigma squared, the population variance is known, then the mean value of the population is located between this lower limit and upper limit with this confidence level. When population variance is not known, that we are going to use t distribution. What about confidence level for sigma squared? We are also, from samples, we are also able to find out the confidence level for the population variance. So from samples, or from sample variance to population variance. So to do that, we should be so we have not learned about this, but in fact maybe you have only heard about its name, but chi distribution is defined as n-1 s squared divided by sigma squared. Sigma squared. So we are, from now on, we are going to use chi-square distribution. And if we use this property, then this will be, so we are going to get the distribution for chi-squared, and in that case so chi-squared for one interval, 1 point lower, so chi-square value for one lower limit, and chi-square value for upper limit. So chi-square distribution. So let's think about this example of k equals 3. So it has this shape. Starting from 0, it gradually increases, and then it starts to decrease. And usually chi-square distribution give us the area under, so it depends also on textbook, so we need to check the textbook first. So in our table, in appendix A, we have the table for normal distribution. This would be the distribution for standard students t distribution, and then this is the how tabulated chi-square distribution is given in tabulated form. And chi-squared distribution is given as the area. So the chi-squared distribution is given as the area starting from here to the positive infinity, so that when this area becomes alpha, then this value is given as 1 minus alpha. In other words, if this area becomes 95%, then it is called as chi-squared it is called as chi-squared 1 minus alpha. I'm not sure whether this is consistent with the data given here. So it gradually increases as alpha value increases, the chi-square tabulated value also increases. So this seems to be correct. So in case of a two-sided case, then we need to find the one point here, and we are going to find out the point that the area up to this point becomes half of alpha, and we are going to place 1 minus alpha here, and then we are going to place another half of alpha probability to the right tail, to the right hand side, to the upper we are going to place, once again, so the probability of 1 minus alpha will be located at the center, and here we are going to place half of alpha probability, and once again we are going to place half of alpha probability here, so that the sum of these two becomes alpha. And by doing that, we place 1 minus alpha at the center of this chi-square distribution graph. So what it means is that we need to find out first the point that chi-square, this integration, the probability becomes half of alpha. So left hand side, lower limit will be chi-squared of half of alpha, and the upper limit will become chi-squared of, so up to here it should be chi-squared value of 1 minus half of alpha. So the point is that, so this, for in case of a two-sided case, we should place half of alpha here, and 1 minus half of alpha should be placed here, and the area between these two values, will be 1 minus alpha. So with this, if we know the sample variance, then we will be able to specify the interval that the population variance is located. So we are going to divide both sides with n minus 1. So 1. And then s squared. So we are going to divide both sides with s squared. And we are going to change the numerator and denominator in all the terms. So in that case, we should change the direction of inequalities. So if it becomes sigma squared, then let me first do that. And this is placed in the numerator, now becomes denominator. The denominator now becomes a numerator. And of course we need to change the direction of inequalities. So this would be equivalent if we change the direction of inequalities to the direction that we are familiar with. This should be placed to the left hand side, this one to the right hand side. And now the equation becomes same either one that is given in our textbook. So what does this mean? That means by sampling from samples, we are able to calculate sample variation. And then n is the number of samples, and chi-square value could be found from the table in Appendix A. So the range, the interval that the real population variance is located can be specified with confidence level 1 minus alpha, that this population variance is located between the lower limit and upper limit with associated confidence interval. So confidence level. So this confidence, like 1 minus alpha confidence interval can be specified from samples. So today we talked about estimation. And first we started from point estimation, and then after the break I talked about this interval estimation. And in this interval estimation, these confidence intervals are provided for the parameters, for unknown parameters that we would like to find. And in that case, not only the confidence interval, this confidence level is associated with that confidence interval. So another thing, if I emphasize one more time, then so if we increase the size of interval, so if from the first to second, if we increase the size of interval, then we are able to that means we increase the confidence level. In other words, if we increase the confidence level, so actually the inverse is also true. So if we increase the confidence interval, that means from 0.95 to 0.99, from 95% to 99%, then we increase the size of interval. So we actually widen the interval that the unknown parameter is located. So this would be the how interval estimation is performed. And based on that, next time we are going to talk about hypothesis testing and all other topics. So this would be end of today's lecture, and I will see all of you next Wednesday.